Hello, welcome back. Previously, in Introduction to Machine Learning, this little series, I went over what the three groups or types of machine learning algorithms are: reinforcement, unsupervised, and supervised. And I mentioned in that previous video that I was going to go a little bit deeper into each of the three groups of algorithms. However, I figured I went over so much detail in those groups already in that video that I decided that I want to go a little bit deeper into, after you've chosen what group your problem is associated with, where do you go from there? You choose your algorithm, you train a model, and then how do you diagnose it? How do you see, okay, is this performing well or not? So that's what I want to talk about in today's video. I'm going to be going over what overfitting is and looks like, what underfitting is and looks like, as well as if you've just looked at your problem, you know it falls into one of your groups, how do you choose an algorithm, and what would be the best way to train a model for that algorithm, and what might that look like. So that is what I will be going into here. So to kick things off, let's say that you just got your problem, you know what group you want to go into. We'll say supervised machine learning. How would you go about choosing the algorithm and then training that algorithm for your problem? So in this case, we'll say your problem is just say P in this case. And let's say it's a fairly simple problem and you think you might be able to start with a decision tree. So we'll say you start with a decision tree algorithm for your first algorithm you try. So you've collected your data. So you collect your data and you format it. You get into a little data set that you have. Now, what do you do with your data set? Well, this is where it's usually an 80-10-10 split. You can do it differently. There are different ways. However, I've usually done, say, an 80-10-10 split. And what this refers to is your training data, your validation data, and your test data. So you would have 80% of your total data set dedicated to training your algorithm, 10% to validating, and the other 10% to testing. So what do each of these three terms mean? So to just kind of go over those three terms real quick, if you're thinking of training, that name kind of speaks for itself. This is the data that you give to the algorithm to actually train. So if you're, in this case, running a decision tree algorithm, you'll take 80% of your data set, you will feed that into your decision tree to train on, and that's what that 80% is going for. In the next part, you'll be thinking of the validation data. And so what does this validation data set mean? That's 10% of your data set. What does this 10% do for you? So this is data to test your newly trained model. So to test your model. And when I say model, just to kind of also point this home, is that you have your machine learning algorithms. Every time you train an algorithm, you get a model out of that. So you take an algorithm and you train it and you get a model from that algorithm. And that model is what you want to test. So you go and then test your model on this validation data set. And then once you've done your testing, you think your model is trained properly, has all good hyperparameters and whatnot, then you move on to your final test data set. So the final data set that you have, the other last 10%, is what your final keyword here is final testing is done on. And so the way you want to think about this is your algorithm will technically be training on these training and validation data sets. So as you're going along, you will train the algorithm, and then at the end of it, you will validate it. If the validation accuracy is high enough, then you might move on. If your accuracy is not very high, then you'll go into diagnosing, which I'll go into with overfitting and underfitting here in a minute. But then you'll do your iterations on your model to get a better accuracy on your validation data set. You do not want to test on your test data set until you think you have a good validation accuracy. So that's the main thing, and that's why I say final here and have it underlined, bolded, and everything, is because you don't want to use this part of your data until the very last minute. That's how you're actually testing your data and making sure it's okay. So, because say for example, we would do a 90-10 split for training and testing. Say you have this 90-10 split. Well, you train on your 90 and then you test on the 10% for your testing. Well, in this case, you are going to be fixing your algorithm to make it optimally fit that 10% test data set. That's what your goal is going to be. But you have no way of knowing if that's accurate. So what you can think about it is you've trained it, you have this training done on your model, you go and test it, and look, your accuracy is, say, 80%. And you say, okay, this is actually really good. And so you go to either maybe turn it in as homework, or you give it to a client or your boss, or maybe you're doing a startup and you run it. Whoever you give it to then comes back and says, hey, I'm only seeing a maybe 46% accuracy here. Why? I thought you said this had 80% accuracy. Why am I getting 46? Well, that's because you were trying to fit the model to your test data set, and you have no other real world or other data examples to say whether or not that's correct. And so this is why this 3-80-10-10 split is important, and why you always want to have a training, validation, and test split is for this very reason. So you can do training and you're doing your validation, so you're fine-tuning your hyperparameters, or you're looking at overfitting and underfitting. Like I mentioned, I will get into those in a minute, but you work with your model, you work with the algorithm to maximize the accuracy of your model on your validation, and then you go and do it on your test data set, and you see that once you see that your test data set then has a high accuracy, that's when you know that you have succeeded. If it does not have a high accuracy, then you know that you've kind of overfit a little bit, and that's kind of getting into it, getting a little bit ahead, but overfit your validation data. So this is where you might start. So like I mentioned, maybe you have this problem P, you pick a decision tree because maybe you think it's a fairly simple task, simple problem. You collect your data, you make your 80-10-10 split, and then you go you train your model, and you find out that it's not working very well. You've trained it, you've done some fine-tuning, and your validation error is pretty high. So what then? What do you do at that point? Well, then you diagnose the problem, and then you see, okay, do I need to change something in my decision tree algorithm? Maybe there's some hyperparameters that you need to tune for your decision tree, and you go back and change those. Or you might say, well, maybe I need to get more data. Maybe I don't have enough data. Or maybe my data is too simple still, and you need to add complexity to your data. And finally, maybe decision tree algorithms are just not good enough for your problem. Maybe your data is so complex that the decision tree algorithm could not properly work with your data. And so you decide to maybe move to a different algorithm. Maybe you move to either a random forest or even possibly a neural network. Maybe you find, okay, maybe it's so complex, you try a few options, you end up moving to a neural network. And so at that point, you might finally get to a point where your test data set shows that you have a high accuracy, low error, and you might be good then. And so just to kind of think this over here, this whole process that I just mentioned of you start with this problem, you start with an algorithm, you collect your data, you have to format your data for that algorithm possibly a little bit, you make your training validation test split, you train, you do some iterations on that algorithm, maybe you move to a new algorithm and do that all over again. This is just to say that, and I'll change this up here, machine learning is iterative. So that's the main takeaway from this whole part, besides the training, validation, and test, is that machine learning is iterative. You will never, or almost never, be able to have a problem, come up with an algorithm that you want to use, train the algorithm into a model, and then be done. There will always be iterations you can do. Iterations, maybe changing hyperparameters, maybe changing some of your data, maybe collecting more data, maybe changing to a different algorithm. There will always be iterations, and that's not bad. That is a good thing, because then that gives you more of that experience that I mentioned before of this is what would work for this type of data. This is what won't work for this type of data. And it'll also give you more experience with these algorithms as well, because then it might give you a sense of, okay, if I change this hyperparameter with an algorithm, it will give me such and such results, and now you know how to work with that hyperparameter more later on. If you come back and see if you need to maybe use that specific algorithm again for a different problem. So that here, these two things are the main takeaways from here. Machine learning is iterative. You will start one place and you most likely will end up in a complete other place. There's always defaults for every algorithm. You can start with the defaults and see where you end up, and then you will go back and change those default values for those hyperparameters and try other ones. And as well is that there should always be this 80-10-10 split. And if you want to go a little bit deeper into that, usually you can, if you don't want to do this 80-10-10 split, there's also been you can look into cross-validation. That is another option. And that's does more or less the kind of 80-10-10 split, but it works also iteratively while you're training and testing your algorithm. So I can maybe go into that in a little bit more detail in another video with some examples on that. But that's another option that I should also think should be pointed out at this point, at this stage. And so this is how you would want to get started with machine learning. So as I mentioned, it's very iterative. You're doing a lot of training and validation. And I mentioned you want to make these changes depending on what you diagnose. So the question is, I said iterative. I've said that you might make these changes. How do you know what changes to make? And that's in determining if your algorithm is overfitting or underfitting. And so next here, I'm going to go into overfitting your algorithm. So now let's move on to overfitting and talk about what overfitting actually is. And another way of saying overfitting is that your model has high variance. So if you're talking about having an overfitting problem, you're meaning that your model has high variance associated with it, with your training and your validation error. And so that's what overfitting means, is that your training error is low while your validation or testing error is high. And if we want to try and plot this out on a graph, what we could try and do is first say that you might have, say, m data points in your data set. So m is the size of your data set. And we want to plot on a graph. Say this first point here is one complete training of your model on one of your data points. This second 2 here is training your model separately on only 2 data points out of your whole data set, and then separately training on 3 data points out of your data set, and so on up to m data points. So then you would have all data points in your training data set. And then on the left hand side here, the y-axis is your error. And so what you would, more of a steep here, is you would have 2 lines. You would have the bottom line here being the training error, and this top line here being your validation error. And so the main thing you want to take away from a graph like this is you would notice that there's a very large gap between your training error and your validation error. That's as you're gaining more and more data points into your model, as you're training your model with more and more data points. And so this is a good way of showing just your algorithm at work. You're training it and you see, okay, this is my training error and validation error, and it's not right. There's something wrong here. And you might take just a snapshot here, see at this endpoint, and you would see, if you just took a snapshot, say you didn't build this entire graph out, because that might take a while if you have a lot of data points. So instead you might just train it completely on all of your data points, and you'd see that your training error, your validation error is very high, and your training error is very low. That would be your sign that your model is overfitting your data set. And so what do I mean when I say that your model is overfitting your data set? So a good way of describing a model overfitting a data set is that it can perfectly train or almost perfectly train and predict on your training data set, but it cannot do well on any other new input. So let's think of it like this. So you have, say, a set of chairs. Maybe you're making a model, an algorithm to predict whether you see a chair or not. And so you might have some set of crudely drawn chairs here, so on. So maybe this is one chair and you have a whole data set of chairs. Maybe this is another, maybe a recliner here. You have this being the back, and you have a cushion along the bottom here with your legs. That looks more like a piano. But you have maybe a data set of chairs here, and you want to train it to predict on chairs. Well, if you train it on, say, these two chairs here, it would learn and it would be able to say these two chairs. If you give it any picture similar to these two chairs, it would automatically say, yes, this is a chair. It would be able to predict that very well. But let's say that you have a different chair. Maybe you have one of those hand chairs where you might have something like this, and then it would be going around the bottom here. So you have a hand chair like this, and you pass a picture of this hand chair into your algorithm. It would randomly guess more or less because it doesn't know what this chair is. It cannot generalize to any other chairs. It can guess on specifically these chairs perfectly fine, but it cannot generalize to any chair. So that's what you might be looking at when you have this overfitting problem. It can predict the training data set extremely well, but any new data point into it fails. It will just basically be randomly picking, or maybe even worse than random, if it thinks everything is not a chair at that point. So it might actually do worse than just randomly picking. And so that's what you would have for overfitting. So then the question becomes, okay, if I can see I've either been able to clearly see that, okay, yes, I have my training data set and validation data set are somewhat different, and so I've been able to clearly see that it can't predict any of these validation data points, or you plot your error out onto a graph and you see that it's not doing anything at all, then, or it's having this type of output here with a very large difference between your validation and training error, then there's three possible options that you have to fixing this overfitting problem. So one of the problems that you can use, and this would be the first one that you want to try, is if your problem has a learning rate if your algorithm has a learning rate associated with it, then you want to try and increase that learning rate. So maybe increasing that learning rate as you're training it could get away from this overfitting problem. That's the first thing you want to try, because that's the easiest thing to try. Because remember, as we're going through these fixes, you want to think of, okay, I'm doing an iterative approach here. What's the quickest and most efficient way that I could try and change what I'm doing to get a better outcome? So in this case, the quickest way would be to maybe try and increasing your learning rate and seeing if that gets you possibly a better result. The next option that you might be able to try And this is another more simple option, is try to add regularization. Always have a hard time saying that word. So try to add regularization. And this is something, it's not too difficult to work with. And that's why I say it might be your next option. But I might be able to go into this in a future video where I talk about what is regularization and how do you implement it in with your algorithms. And so really, number 2 here is more often than not the first thing that you'll try if you're not working with an algorithm that has a learning rate. But there is a third option that's not always available depending on what your data set is, but it is something to remember, is to try and remove your features, some features in your in your entire data set. So try to remove features in your data set. And I mean your whole data set. If you've already split it up into a training, validation, and a testing data set, recombine all those and try and think of a way to remove features. Now, as I said, that might not be very possible. If you're working with pictures, it most likely wouldn't be possible unless you try and shrink the number of pixels per picture down. If you're working with maybe just some, say, student data, as I mentioned as an example in the previous video, it might work okay with that. If you might be able to say, okay, maybe we have too many classes we're trying to have per student, so maybe we'll try and remove some of the grades just to see if we can improve the prediction. Or maybe you're including standardized tests, maybe you could try and remove those and see if that improves. That is an option, but like I mentioned, this is more of a harder option to implement, so you might not be able to use option 3 all that much, but it is something to still remember. So in the end, this is overfitting. This is how you can look at it. You can plot your error for your training and validation error and see how that looks to see if you have overfitting or not. And then here you also have 3 options to fix the overfitting problem that you might have. One last thing that I actually want to point out before I move on to underfitting is that there is one more fix that you can do. This may be easier than removing features. So this might go before removing features, or it might be easier. It all depends on your data. So option 3 and 4 here may be interchangeable depending on your data set. So that's something you might have to figure out. But number 4 in the fixes that you might have are adding data. So adding additional data to the data set that you have. Now, this, again, depending on what your data is, you might not be able to collect more data. So maybe removing features might be better. Or maybe your features are extremely hard or impossible to remove, so maybe you might be forced to add additional data if you need to. But this is also something that I want to go into more in depth in another video as well, because there are some techniques that you can use to get more data automatically. So you can actually generate more data for your input data set. So that's something that I also will most likely be making a video on in the future, is how might you go about automatically generating more data for your data set. And so now moving on to the last thing that I want to go over is underfitting. And so when talking about underfitting, another way to say this is that your model has high bias. So what do I mean here when I say that your model is underfitting your data set? And that is when both your training and your validation error so both errors are both high. So that's what it means when you're underfitting your data set for your model. And so moving on from here, similar idea to what we had before. Say we have M, which is the training your data set size. So I'll just say number of data points in your data set. Similar to what I mentioned about in overfitting. This is the same M, just like over in when I was talking about overfitting. So what we want to do is we want to, again, just like in overfitting, plot out on the y-axis here the error, and on the x-axis we want to plot out what it would look like to train our model separately for 1 data point, 2 data points out of your data set, 3 data points out of your training data set, and so on up to all M. So you want to do this, and you want to capture the validation error, and you want to capture the test error, or training error. So this lower one here is the training error, and this upper one here is the validation error. And you'll notice that both of these are high. And so similar to what we mentioned in the overfitting, say we want to not do all this, maybe you just want to get a snapshot and just train for over your whole data set. Then maybe you want to get a snapshot and you see these data points and you see that both the validation and the training error are both high. That's how you know when you are underfitting your data. And so what's another way to kind of say underfitting? Well, another way of putting it is that your model is basically guessing for every input that it does not know. So for every input that was not in your in your training data set, it most likely will be guessing. So for every input that you did not have in your training data set, it most likely will be guessing on that input. And just another way to put it, to make it maybe a little bit more concrete, like I did an example for the overfitting. Say, for example, you have a training data set that are just some chair legs. Pretend this is just some chair leg. You're not sure where the chair leg is from, but it's a chair leg. You have a data set, a training data set full of these chair legs here. And then you go to, in your validation data set, you might have a chair leg that looks like this. So one of those chairs that just has 2 legs on it that have a U shape to them. So say that this is in your validation data set. So your model will be trained on this, and we'll basically be guessing on this. It might say it's a chair leg or a chair come from a chair. It might not. It's most likely just going to be guessing with that input. You're basically giving your model a single picture of a chair leg and expect it to know every single type of chair leg out there. So that's what you're kind of expecting your model to do. And just like with overfitting, you do have a few options to fix this. However, they're not as easy. So you have two options. The first option is to add additional features to your data. So as I mentioned before, in the overfitting dataset, I mentioned having the student data that you trained on, and in that case we were removing data points, so we thought maybe you might want to remove test scores, or maybe there's some class grades that you don't need, so you can remove those. Here we want to do the opposite. We actually want to add more features. You want to make your data more complex, and that way your algorithm might be able to get more input out of each data point. So for example, maybe we want to, instead of just giving one chair leg, give a picture of the entire chair. That would make the pictures more complex, and then it might be able to more easily interpret and make correct predictions on what other chairs might be. So you want to make your data more complex by adding more features to it. And your second option for your fix is to try a more complex model or algorithm. So in this case, say you're starting with the decision tree like I did in the example, and you might see that it's overfitting. You might get a result like what we have here. You might see that it's, or underfitting, I mean. You see it's underfitting, you know, okay, I need to add additional features. Maybe my data is set in stone. I can't add anything. I can't change my data at all. Well, you know, your option then is you either want to make your tree more complex, so allow it to have more leaves, more branches, larger tree. Make the model in that case more complex, the model being the tree. Or you can get a more complex algorithm. Maybe move on to random forests, or move on to a neural network or something else. So that would be your two options in this case, because this is basically saying that your model and algorithm that you currently have cannot support, are not complex enough to be able to understand what data you're giving it, or your data is not properly, there's not enough information per data point to answer your question that you have with your problem. So this is everything to deal with underfitting then. This is, you have very high training and validation error, and you want to either increase the number of features or make your data more complex, or you want to make your algorithm or model more complex. So just to wrap everything up, I've gone over just the fact that machine learning is iterative, how you want to split your data set up into the three parts with the 80-10-10 split, gone over what overfitting is, what underfitting is, but there is one thing that I did not mention, and that is the fact that I've given you both of these sort of graphs of what to look for when something is wrong, but what about if something is right? Because the thing with machine learning is also this, the fact that you will never ever get 100% accuracy in your validation data set. And so the best thing you can do is just hope for the best validation error, while making sure that when you go and do your testing and dataset that you actually have a low testing dataset error as well. And so using those same sort of graphs that I mentioned in the overfitting and underfitting, so if you have the 1, 2, 3 data points all the way up to m data points, just like in those other two examples, you want to have something here in the middle. This is what you're striving for with your validation and your training errors. So that's just the thing to know, is you will have error. It's a matter of machine learning. It will always be there. You will never have 100% accuracy. So you want to improve your validation error, and in improving your validation error, you're making your algorithm more generalized. And so while you're making it more generalized, that means it will have more error in your training data set. So that is why you will see this training error line actually going up while your validation error line is actually going down. This is something you want to see. You want to see them meeting somewhere at or below this kind of 50% line here. So if we draw this line all the way out and say that this is, say, 50% error, 50% accuracy, in this case they both be the same, you want this to be at or below this line, basically, both of these, validation and training error. That's what you'll be looking at mostly for machine learning. And like I said, it's an iterative approach. You might start off small, see your underfitting, move to a bigger algorithm, see your overfitting, add regularization techniques, still see your overfitting, maybe add new data, see your underfitting. So maybe you might try to add more features to your data set, and then at that point you might be good to go. So that's the iterative approach. You had, in that case, there was about 4 or 5 steps. So that's what I'm talking about, iterative, that machine learning is iterative. That's what I mean. You might think, okay, this might work best here, but it will change. And so that's just the one thing to know, is nothing will most likely ever, I don't like working in absolutes, but nothing most likely will ever work right the first time you try this. And that's just something that you will get used to, and you will not only get used to, but you'll learn how to cope and work with diagnosing that error that you do find, to work it and make your algorithm better every time that you train. So with that all said and done, I've now gone over and worked over how you're going to be starting a problem in machine learning. I've gone over what overfitting is, what underfitting is, how you will be actually working with these overfitting and underfitting to iteratively incrementally have better accuracy for a problem that you have, and what to expect when you're finally done. So the next thing that we'll be talking about in the next video is one of a few things. It might either be underfitting, or I'm sorry, it might be not underfitting. It might be talking about either regularization, it might be talking about automatically getting new data, or it might be just talking about something else for machine learning, because there are a few other topics that I want to go through, such as what's a skewed class and how to work with that with whatever accuracy parametric that you're working on. What's the best one of those to work with? So if you have any suggestions, leave them in the comments, and I will try and look at those and see what other people might be interested in learning here next. So with that, thank you very much.